Hi guys, I hope you survived the lecture on regular expressions and finite automata. And now we move on to the asynchronous lectures of week 11 of CSCI C311 programming languages. It will focus on scanning, which is the first phase of compilation. And in this phase, it will use the knowledge of regular expressions and finite automata. After this lecture, you will be able to explain how scanning you will be able to explain how scanning as part of learning how scanning works. You will also learn how scanning works. You will also learn an algorithm non-deterministic finite automaton into a non-deterministic finite automaton into an equivalent the materials of this lecture are based on section 2.2 in the textbook. One example showing the conversion from an NFA to a DFA was taken from my lecture of the CSCI B401 course. Recall that together, the scanner and parser for a programming language are responsible for discovering the syntactic structure of a program in that language. Scanning or lexical analysis is the necessary first step toward translating the program into an equivalent program in the target language. One main responsibility of the scanner is to tokenize the source program. By grouping input characters into tokens, the scanner dramatically reduces the number of individual items that must be inspected by the more computationally intensive parser. Another responsibility of the scanner is to remove comments, so the parser doesn't have to worry about them appearing throughout the context-free grammar. In addition, the scanner saves the text of interesting tokens like identifiers, strings, and numeric liberals. It also saves source location by tagging tokens with line and column numbers to make it easier to generate high-quality error messages in subsequent phases. In some language, a program can contain constructs called pragmas that provide directives or hints to the compilers. Pragmas that do not change a program semantics, only the compilation process, are sometimes called significant comments. In this case, they are usually processed by the scanner. So that is an additional task for the scanner. As an example of scanning, we consider a simple calculator language with input, output variables, and assignment. The tokens for this language can be defined using the following grammar rules. Each rule defines one token, where the left-hand side of the arrow is the name of the token, and the right-hand side of the arrow is the regular expression that generates the token. So here we use colon equal size instead of just equal size for assignment, in keeping with the Algo language and its descendants, as opposed to C* languages. We have also listed tokens, read and write, as exceptions to the rule for ID. To make the task of the scanner a little more realistic, we add tokens for comment in our calculator language. This rule for comment is borrowed from the two styles of comment in the C language. The first style is for multi-line comments, which is the one between a forward slash and an asterisk and an asterisk and then forward slash. And the second style is the just the end of line comments, which starts with a double forward slash. So here non-star denotes any character other than the asterisk, and non-slash denotes any characters other than the forward slash, and non-new line denotes any character other than the new line character, and new line just denote the new line characters. Okay, so here note that there are two asterisks here. The asterisk that is written as the superscript is the clean star, which denotes the clean closure for the regular expression. So this just means that this is a zero or more concatenation of non-new line characters. Right? And so, for example, here this asterisk is also the clean star or clean closure, and the this asterisk up here is also a clean star or clean closure. But the asterisk in in the same line as other normal characters is the character itself. So how may we go about recognizing the tokens of our calculator language? The simplest approach is entirely ad hoc. We can structure the code however we like, but it seems reasonable to check the simple and more common cases first, and then to pick ahead when we need to, and to embed loops for comments and for long tokens such as identifiers and numbers. After finding a token, the scanner returns to the parser. When invoked again, the scanner repeats the ad hoc algorithm from the beginning, using the next available characters of input, including any character that were picked at but not consumed the last time. As a rule, we accept the longest possible token in each invocation of the scanner. For example, the 3.14 could be recognized as a single token representing a real number, and never as 3 tokens, 3, the period, and 14. And white space, including blanks, tabs, new lines, and also comments, is generally ignored, except to the extent that it separates tokens. Suppose we are building an ad hoc scanner for our calculator language. On the right side is the first part of the pseudocode for this scanner, which recognizes the tokens defined as in the rules on the left side. So we read characters one at a time with lookahead, skipping any initial white space, including spaces, tabs, and new lines. If the current character is one of the one character tokens, including the open parentheses, close parentheses, plus, minus, and asterisk, Then we return the corresponding single character token. If the current character is a colon, then we look at the next character. If the next character is an equal sign, then we return a sign. Otherwise, we announce an error. This is the second part of the pseudocode of the scanner for our calculator language. This part recognizes the tokens defined as in the rules for division and comment. So in this part, it checked if the current character is a forward slash. If so, then it picks at the next character. So here note that it only picks, not reads. And if the picked character is an asterisk, then it reads additional characters until a sequence of an asterisk and a forward slash is seen. If the picked characters is a forward slash, then it reads additional characters until a new line is seen. Okay? And then after that, in other case, it jumps back to the top of the code, which is in the first part of the pseudocode. Otherwise, it just return div. That is when the picked characters is neither an asterisk nor a forward slash, then it just return div, which stands for division. The last part of the pseudocode of the ad hoc scanner for our calculator language will recognize identifiers and number tokens. So it checks if the current character is a period, then it reads the next character. And if the next character is a digit, then it reads any additional digits until it enters a non-digit character, at which point it returns a token number. Otherwise, it announces an error. So this is the case when the next character after the period is not a digit, then it announces an error. Yeah. So in the case that the current character is a digit, then it reads any additional digits and at most one decimal point. Then after that, it returns a number. In the case that the current character is a letter, then it keeps reading letters and digits until it can't anymore. Then it checks to see whether the resulting string is a reserved word, read or write. If so, then it returns the corresponding token, read or write. Otherwise, it returns the token ID. And in any other case, that is in the case where the character is not one of these and it didn't lead to any return earlier, then it announces an error. Note that production compilers often use such ad hoc scanners because the code is fast and compact. During language development, however, it's usually preferable to build a scanner in a more structured way as an explicit representation of a deterministic finite automaton, or DFA. Recall that regular expressions generate a regular language, and the DFAs recognize that language. And so in the DFA approach to scanning, after we represent the scanners as a DFA, then we run the machines over and over to get one token after another. And here we also apply the longest possible token rule. That means that the scanner returns to the parser only when the next character cannot be used to continue the current token. As an example, this is pictorial representation of a scanner for calculator tokens in the form of a DFA. This DFA is handwritten. Its state diagram roughly parallels the pseudocode of the ad hoc scanner. Scanning for each token begins with the start state, which is state 1. The final states in which a token is recognized are indicated by double circles. So here we also write the name of the token next to the corresponding final state. Comments, when recognized, will send the scanner back to the start state rather than a final state. So here at the start state, if it sees the forward slash, then it will enter the state 2, which is the final state for div, for the token div. And if you continue to read, and if the next character is forward slash, then it enters the state 3. When it's a state 3, if it see any non-new line character, it will stay at state 3. And when it sees a new line characters, then it go back to the start state. So it start over to read the next token. And when it's at state 2, if it see the next characters and it is an address, then it enters the state 4. And when it's a state 4 and it sees any non-address characters, then it still stay at the state 4 until it sees an address. Then it enters a state 5. When it's at state 5, it will stay at state 5 whenever it sees an address. Okay. Otherwise, if it sees a non-address and non-forward slash characters, it will go back to state 4. And when it's at state 5, if it sees a forward slash, then it go back to the start state, because at that point it just finished recognizing a multi-line comment. While we can handwrite a DFA for the tokens of a specific language, finite automata can be generated automatically from a set of regular expressions, making it easy to regenerate a scanner when token definitions change. This is particularly useful during the language development because token definitions may be changed when the language has not been finalized. This task of generating a finite automaton from a set of regular expressions is performed by scanner generator tools such as lex and flex of units. Lex is the standard lexical analyzer generator on many Unix systems. It was described in 1975. Flex, which stands for Fast Lexical Analyzer Generator, is a free and open source software alternative to Lex. It was released around 1987, which is 12 years after Lex. Recall that there's no algorithm to directly translate from a regular expression to an equivalent DFA. The algorithm for automatically generating a DFA from a regular expression would go through 3 steps. The first step is to convert the regular expression into a non-deterministic finite automaton, or NFA. We had discussed the algorithm for this step in the previous asynchronous lecture. The second step is to convert the NFA into an equivalent DFA. The third step is a space optimization that generates a final DFA with the minimum possible number of states. In the previous lecture, we had learned how to convert from a regular expression to an NFA. Now we will learn how to convert from an NFA, such as this machine, to an equivalent DFA. We can use the set of subsets construction to transform an NFA into an equivalent DFA. The key idea is for the state of the DFA after reading a given input to represent the set of states that the NFA might have reached on the same input. More precisely, each state of the DFAs is a subset of the NFA's set of states. For example, so consider this NFA, which has 3 states, 1, 2, 3. So then the DFA that we will convert into will have states, each of which is a subset of the set of 1, 2, 3. So it includes the empty set, and then it also includes the subsets that consists of just one member, that is just the subset of just 1, the subset of just the state 2, and the subset of just 3. Right? And then it also contains the subsets of 2 members, such as 1, 3, 2, 3, and 1, 2. And finally, it also contains the subset that is equal to the entire set of 1, 2, 3. So there are 8 subsets of the sets of states of the NFA. So the DFA has 8 states like this one. Okay? And for each subset X of the NSA set of states, which is a state in the DFA, then so each of such subset makes transition on a given input symbols, such as A or B in this case, to the set of states that the NFA can reach on the given input symbol from a state in X. So, for example, if X is the subset consists of 2 states, 1 and 3 of the NFA. Okay? And we consider the given input, which is the input symbol B in this case. So then we need to identify which stage of the DFA this transition will lead to. So to identify that a state of the DFA, we look at which states of the NFA that you can lead to from each of state in the set X. So for example, here we check from state 1, where can we go on the input symbol B. So from 1 we can only go to number 2, right? And so from the state 3 here, and on the input B we cannot go anywhere. So from the stage 1 and 3 we can only go to the state 3 on the input symbol B. So the transition from the subset of 1, 3 on the input B will go to the subset that consists of just the state 2 of the NFA. So as another example, so let's pick the state X to be the subset consisting of the state 2 and 3 of the NFA, and we consider the input symbol A. Okay. So now from the state the state 2 of the NFA, and on the input symbol A, it will just go to A, and it can also go to 3. And so then this the resulting set of state must contain 2 and 3. And for the state 3, when it's on the input symbol A, it will go to state 1. So from the subset of 2 and 3 and on input A, it will go to the subset containing 1, 2, and 3, okay, of the DFA. And let's consider another example. So if X is a subset that consists of just the set 2, then in this case it's easy. If we consider the given input symbol to be B, then from 2 and on the input symbol B, it can only go to 3. But if it's on the input symbol A, so from 2, then it can go to 2 and 3. So therefore, the from the subset consisting of 2 and on input symbol A, it will go to the subset of 2 and 3. And so if you consider the set X that consists of just the number 1, so then in this case, if you look at the input symbol B, then from 1 you can only go to 2. And if you look at the symbol A, then from 1 there's no outgoing arrow from 1, so that means that it just leads to the empty set. Okay. And if you look at the state number 3, okay, if the subset X consists of just the state 3 of the NFA, and you look at this current symbol A, so from the state 3 and on the input A, you can go to 1. However, there's an epsilon arrow from 1 to 3. So then you can go from 3 to 1 and then back to 3, just on the input symbol A. Okay. So therefore, from the subset consisting of just 3 and on the input symbol A, it will go to the subset consisting of the state 1 and 3 of the NFA. So this example explains the case of the epsilon arrow here. We have identified the states and transitions of the equivalent DFA converted from an NFA. We still need to identify the start state and the final states of the DFA. So in this algorithm, the start state of the DFA is the set of states that the NFA could be in before reading any input. So those are the states that can be reached from the NFA start state via epsilon arrows as well. So of course it needs to be it needs to include the start state of the NFA. So in this case, the start state of the DFA will include the start state of the NFA, which is 1, and also other state that the NFA can be in before reading any input. So that means that the states that you can reach from the start stage of the NFA via epsilon arrow. So in this case, there's only the state number 3. So the start state of the DFA in this example is the subset consisting of just the state 1 and the state 3 of the NFA. A final state of the DFA is any set of states that contains a final state of the NFA. So here, state 1 is also the only final state of the NFA. So any subset that contains the state 1 will be a final state of the equivalent DFA. So it needs to contain the subset of 1, 3, and then just 1 and 1, 2 and 1, 2, 3. So in general, the number of states in the DFA that is converted from an NFA using the set of subset construction is exponential in the number of states in the NFA. So in particular, if the NFA has n states, then the converted DFA will have 2 to the n states. In this example, n is equal to 3. So the NFA here has 3 states, and the equivalent DFA has 2 to 3, which is 8 states, because the number of subsets of a set of n elements is equal to 2 to the n. To reduce the number of states in the DFAs, we can remove the states in the DFA that are unreachable from the start state of the DFA. So because those states will never be visited in any computation of the DFA. For example, in here, the states consists of just the state 1 of the NFA, and the states consisting of the state 1 and 2 of the NFAs are unreachable from the start state of the DFA. You can see that because there's no ingoing arrows into these 2 states. Okay? It has outgoing, but outgoing arrows, but it doesn't have any ingoing arrows. So we can get rid of these 2 states, and we still have an equivalent DFA. In other words, we can build the DFA from the NFA by starting with the DFA start state, and then adding only states that are reachable from existing states. So first we start with the start state here that consists of the state 1 and 2 of the NFA. So then we explore which states can lead to from the start state on the input A and on the input B. So on the input A, it just go back to the same start state. On the input B, it will go to the next stage, which is the one consisting of just the state 2 of the NFA. And then, so now we have these two states, and then we also have to explore the outgoing transition from these two states to get new states. So in this case, we get to state 3, and also we get to states consisting of 2 and 3, and then and so on. So after you get these these 4 states, then we explore outgoing transitions from these existing states. Then we get new states until we cannot add anymore. So that is just another way to build the DFA from the NFA, but also using the set of subset construction. But at the same time, we don't have to list all of the possible states of the DFA. Here is another example showing the approach mentioned in the previous slide. In this example, we have the NFA that was converted from this regular expression, which generates decimal numbers. This NFA has 14 states, so if we list all the possible states of the equivalent DFA using the set of subsets construction, then we could end up with 2 to the 14, or roughly 16,000 states. Fortunately, in this case, the vast majority of those states are unreachable from the start state of the DFA. So in fact, there are only 7 states that are reachable from the start state of the DFA. So let's see how we discovered them. First, we start with the start state, which is the set of all states in the NFA that can be reached from the NFA start state via epsilon arrows. So they are 1, then 2, then 4, then 5, and 8. We call this state of the DFA the state A for short. Now from the state A, we want to see which state it will transition to on each of the 2 input symbols D and the period. On the input symbol D, we cannot go anywhere from state 1, 4, and 5. But from state 2, we can go to state 3 via the we can go to state 3 on the input symbol D, and then go back to state 2 via the epsilon arrow. Or from 3, we can go to state 4, and then 5, then 8, also via epsilon arrows. From state 8, we can only go to state 9 on the input symbol D. So from the state A of the DFA and on input symbol D, we can only go to the state consisting of 2, 3, 4, 5, 8, and 9. which we call state B of the DFA. On input symbol period, we cannot go anywhere from any state in A except for state 5, so here, and which leads to state 6 in the NFA. So from state A of the DFA, we go to the state consisting of just the state 6 of the NFA on the input symbol period. We call this state the state C. Then we continue to explore outgoing transition from state B and C and discovered a state D and E, and so on. And the final states of the DFA are those containing the final state 14 of the NFA. So they are state D, state E, state F, and state G. We can represent the DFA for a scanner in either of two main ways. One embeds the automaton in the control flow of the program using a loop via the go statements and the nested case statements, which is part of the switch statement in the C, C++ or Java languages. The other way uses a data structure that is a two-dimensional state transition table. As a general rule, handwritten automata tend to use nested case statements, while most automatically generated automata use tables. A table-driven scanner is a driver program that uses two tables. One is the state transition table of the DFA, and the second table which indicates for each state whether it's a final state. That is, we might be at the end of a token. And if so, it also indicates which token. Separating this second table from the first one allows us to notice when we pass a state that might have been the end of a token, so we can back up if we hit an error state. The nested case statement style of automaton has the following general structure. It starts with setting the state to be the start state of the DFA. So in this case, we just assume the start state to be state number 1. Then it goes through a loop. In each iteration of the loop, it reads the current character, then enters the outer case statement, which covers the states of the DFA. The inner case statements cover the transitions out of each state. Most inner clauses simply set a new state, and some return from the scanner with the current token. Note that if the current character should not be part of that token, then it is pushed back onto the input stream before returning. And two aspects of the code typically deviate from the strict form of a formal finite automaton. One is the handling of keywords. The other is the need to pick ahead when a token can validly be extended by 2 or more additional characters, but not by only 1. So we will discuss these two aspects in the next slides. So now let's discuss how keywords handle in a scanner. In most languages, keywords or reserved words look just like identifiers but are reserved for a special purpose. It is possible to write finite automaton that distinguishes between keywords and identifiers, but it requires a lot of states. So most scanners treat keywords as exception to the rules for identifiers. In particular, before returning an identifier to the parser, the scanner looks it up in a hash table or a trie, which is a prefix tree, to make sure that the token, the identifier token isn't really a keyword. So here is an example of a trie or a prefix table. A prefix tree. So it is a tree that show like let's say these are the keywords. So it show how you can reach that keyword. Right. So now we will discuss how to handle the longest possible token rule when you implement a DFA. Recall that the rule about longest possible tokens means you return only when the next character cannot be used to continue the current token, and the next character will generally need to be saved for the next token. In some cases, you may need to pick at more than one character of look ahead in order to know where to proceed. In Pascal or C, for example, when you have a 3 and then you see a dot or period, so you have maybe two choices. Do you proceed in hopes of getting like 3.14, or do you stop in fear of getting something like 3.5? So in measure cases, you may not be able to get by with any fixed amount of look ahead. So here we need to remember we were in a potentially final state and save enough information that we can back up to it if we get stuck later. So that is the general strategy for handling the longest possible token rule in representing the DFA for scanner. The last issue with scanning we are going to discuss is lexical errors, which occur when the next input character may be neither an acceptable continuation of the current token nor the start of another token. In such cases, the scanner must print an error message and perform some sort of recovery so that compilation can continue, if only to look for additional errors. Fortunately, lexical errors are relatively rare because most character sequences do correspond to token sequences. Lexical errors are also relatively easy to handle. The most common approach is to first throw away the current invalid token, and second, skip forward until a character is found, then can legitimate begin a new token, and third, restart scanning algorithm, and fourth, count on the error recovery mechanism of the parser to cope with any cases in which the resulting sequence of tokens is not syntactically valid.